Okay. Hello, I'm Sergi Siso from the STFC Hartley Center, and today I will be presenting a tool called Cyclone that we use to process Fortran and do transformations for weather and climate applications. So, and to run them on HPC systems. So if we look at the trends of processors that we have at the moment in the biggest machines, it's well known that we cannot scale too much the frequency anymore, specifically not in an exponential sense, but we still have more and more transistors. So what the processor designers do with this is two things. First, they increase the number of cores and different parallelism levels in vectorization cores, multi-node. But another thing that happens is that they make much more complex architectures to get more single-thread performance. And there is a scope to specialize different architectures for different workloads. So we have a lot more heterogeneous computing. And that's not only in the future, also in the present. If we look at the top 500 list, we already see that almost all of them have some kind of accelerator on each node. And the ones that don't, like the Fugaku or other systems, is because their CPUs are already very specialized CPUs for HPC. It's not only that they have accelerators, it's that it's a very diverse set of accelerators. You can see that there is different vendors on the CPUs, GPUs, and that's getting even more diverse. We know Intel GPUs are coming, NVIDIA CPUs. There's an European project to use RISC-V accelerators, and there's some people using FPGAs for building these high-performance computing systems. However, when we look at the software, in many institutions, it looks like that there's still a very big percentage of the applications that use Fortran. This is a blog post from Jim Coney that did looking at the UK Archer 2 national facilities. It's difficult to say exactly how many core hours come from Fortran, because maybe Fortran then use a library that is in C, so it might be not super accurate, but it gives a view of the magnitude of the applications that use Fortran. And specifically in weather and climate, I would say that's even bigger in the Fortran camp. From these applications here, at least the and NEMO are weather and climate, both use Fortran. And by the way, the replacement of the and NEMO both can be processed by the tool that I will be presenting today. And the thing is, how do we make sure that all this ecosystem of applications that run on HPC can be ported to this new environment with accelerated computing from different vendors? And it's a challenge because that's competing with other software requirements, especially regarding software sustainability. Usually these applications are built with communities, with people from different institutions and with different expertise. So and they have millions of lines of code. So you really have to care about the productivity, the readability, maintainability. And it's usually not a good approach to make a very concentrated effort to rewrite some of these applications into another language, because then you might be leaving the community behind. While you are rewriting your application, maybe there's like tens of PhD students still doing development in the original code in Fortran. So you really don't want to split the communities. So ideally, we want a single source. We don't want different implementation for different platforms, but with the performance and the parallelization details abstracted. So science people can continue doing the science while HPC people reorganize the HPC bits of the applications. So there is different strategies, and I'm moving a little away from Fortran here to explain the strategies. One is, okay, cannot be done in a single source, we can maintain multiple implementations, and that's a bit what maybe CUDA, HIP, or OpenCL would do. But as I said, that's not very attractive in software sustainability point of view. Then another strategy is using compiler hints or compiler keywords that are descriptive. So it kind of gives the responsibility to the compiler to generate the appropriate implementation for each architecture. But more recently, we've seen these new C++ frameworks like SYCL, Cocos, Raja, and others that use compile time abstractions like the template metaprogramming and others. I'll have to say that the difference sometimes it's a bit blurry, because you can also write like a platform specific in this, but they have the extra power of compile time extractions to try to do this performance portability extractions. And then there's task-based parallelism. There's another model to write data-centric programming by marking the dependencies between different computations, so runtime system can schedule them. Again, it's a bit blurry because SYCL and OpenMP also support some kind of tasking methods. So yeah, the problem is, well, what about Fortran? What of this can we do on Fortran? And the problem with Fortran is that it has much more limited heterogeneous programming capabilities compared to the ecosystem in C++. And especially it lacks some of the powerful compile time mechanisms that the people in C++ can use. So what Fortran has been good, I think, is to adding these directives and keywords like the do concurrent high performance Fortran. However, still with this, you are in a situation where some vendors support some of them, while other vendors support the other. So there is not a perfect performance portable way to write the applications. Although I have to say that during the last couple of years, OpenMP, in my opinion, has got a lot better to do this performance portability. Still, I wanted to mention that there is the option to do preprocessor macros. I have to mention it because it's almost in every big application you will find those in Fortran, and it's compile time, if you will, but they do not compose very well. If you start adding too many things in the preprocessor macros, it really impacts the software sustainability. So the idea is, can we have a solution for this to do the same that C++ does with the template metaprogramming? And maybe we can do that with source-to-source transformations that also happen at compile time. So we at Hardtree, together with the Met Office and other partners, we developed this source-to-source code generation and transformation system that ingests the Fortran from different weather and climate applications. We started with Alfric, the next generation atmospheric model for the UK Met Office, but we've been growing to different applications. And these are usually written in or serial Fortran, or in some cases serial with MPI. And then we process and we generate usually other Fortran with injected MPI and injected OpenMP or OpenACC for applications. And until now, the workload has been Fortran to Fortran transformation. But what I'm presenting today here is that we have a new backend that instead of producing Fortran, produces OpenCL. So we can do ingest Fortran and produce OpenCL. It's a bit of a prototype yet. We just really tested it with one of the applications, Nimolite 2D. More on this later. But the good thing about OpenCL is that it increases the range of architectures that we can target with this backend. For instance, with AMD GPUs and even FPGAs. However, OpenCL gives us portability, but portability is not the same that performance portability. So it is unlikely like a direct mapping from the Fortran to our intermediate representation to OpenCL will give us performance portability. You want to generate a slightly different OpenCL for CPUs and GPUs and really different OpenCL for FPGAs. So our solution to that is that we allow to provide a recipe in our intermediate representation to restructure the code in a way that it's appropriate for the architecture that we are targeting. So our intermediate representation, I'll don't give a lot of details, but we try to design it in a way that it is mutable. It is quite high level in the sense that it is quite close to source code. It's nothing like the intermediate representation that you would find in compilers. And it's intended to be programmatically manipulated. So it has a lot of validations and checks when you do a transformation in the AR to make sure that it's still valid and coherent code. We provide utilities like DAC visualizations of the dependencies analysis on your code, calipers to add performance and debugging tools. We support incomplete information. So if some part of the Fortran we don't understand and we cannot represent, it still doesn't fail. It gracefully can continue by transforming the other part of the code. And then these things that we don't understand are maybe optimization barriers for us, but we still can produce a whole application and optimize just part of it. And by itself, it's domain agnostic, but we have a way to extend our AI to add domain-specific knowledge about the applications that we process. So the full workflow is something like this. We have two entry points. One is the scientific domain knowledge written in Fortran. And then we have a second entry point, which are these recipes that explain how to transform our AR. And that's in purpose. We don't want to do like an automatic parallelization. We want to still give the control to the HPC people. This might be different people working in the scientific domain and the parallelization, but sometimes it's the same person, like having two roles. It's the same as if you write a web page. You might write the whole web page, but you write the HTML in one place and the CSS in the other. So it's the same concept of having two separation of concerns. It gives us performance portability because we can have different recipes for different architectures. And still it produces a standard Fortran or OpenCL so that the output is readable maybe in quotes. But the important thing is that you can then plug the standard debugging and profiling tools and try to understand what has been generated. And it's important that we generate the standard code as well, because then we can use vendor compilers or vendor tools to process whatever we generate. There is one more thing that some of our applications use what we call SYCLCON, which is a Fortran kernel-based code structuring model, which is kind of resemblance to what OpenCL and SYCL do, in the sense that we split our application in different layers. These are the algorithm, the parallel system, and the kernel layers. These are these together from the SYCL name. And the natural scientists, the scientists just write the algorithm layer, which is a higher level global view representation of the algorithm. You can see that it's here. It's an invoke with a list of kernels, and we just pass objects that represent full fields. And then they write the kernel, which is the computation to do to a single element of the grids. So the kernel has some JI, JJ to specify the element, and how the things that the algorithm, the global view, is connected to the local view is through this parallel system that tells where each kernel should be executed, in which order, and all these performance important characteristics, and also how to parallelize these kernels. And for that, SYCLCON reads the algorithm and kernel and automatically generates this middle layer for the applications. So nobody writes the middle layer explicitly. It's our tool that generates it for the applications. And the good thing is that this model is quite relatively easy to map into OpenCL because it's kernel based. So what we do is we transpile the kernel code from Fortran to OpenCL, but the kernel code is mostly computational stuff, arithmetics, some math libraries, and data accesses. So we don't have to transform the whole transpile whole Fortran. That would probably be unfeasible. We just to transpile the kernel code, and the things that we don't understand, maybe hoist them to the algorithm code. Also, the accesses to the libraries are in the algorithm code, and it's just transformed from Fortran to Fortran, so it's much easier. And then in the parallel system that we create for OpenCL, we do using the CISO interface from Fortran to C calls to the Fortran runtime, which calls the transpiled kernels. And here is a very, very simple example, as simple as I could make it to fit the code in the slides. So what the application developer would write is the things on the left. So it would write a kernel in Fortran and then a recipe in Python that tells how they want to optimize it. What they usually have to do is two steps. One is to convert the globals into kernel arguments, because from OpenCL we cannot access the global variables, so they are converted into kernel arguments in this first line here, and then request that the whole kernel is transpiled into OpenCL. And then what will happen, and that's how you execute our tool. It's Cyclone plus -s and the transformation recipe, which is here, and source is the original source code that we are transforming. And what it will generate is a representation of the kernel in OpenCL language, plus some Fortran with calling these wrappers into the OpenCL runtime. As I said, that's the basic. That's like the one-to-one mapping, not optimized. That probably will not run very fast, but it's a first step. To run it fast, we have to add more optimizations, and we do that in our transformation script. And basically, the two important ones are kernel blocking, that's adding the block sizes for the OpenCL, depending on the architecture. And the other one is boundary masking. That's because in our applications, we usually have like different layers of boundaries or halos from the MPI, things like that. And they tend, scientific people tend to write them as kernels with multiple return statements, which is not ideal. And they don't start at the first element, the computation. They might start like 2 or 3 layers in. And we found that it's much better to traverse the whole iteration space, no matter if there's boundary conditions or halos, and instead of starting later, unmasking the things that we don't want to update. And we do that automatically with these transformations. So we add these maskings in each of the kernel OpenCL kernels. Another benefit than that is that then if the size of the domain doesn't match the alignment that we want, we can add padding, and the masking will just ignore the padded elements. So that makes it much better for CPUs, for GPUs. So I will now show some results of this with Nimolite. Nimolite 2D is a mini app of one of the components of the NIMO model. It's a oceanic simulation, and well, it's not huge. I think in total has a few thousand lines, but the important ones the ones that we were transpiling from Fortran to OpenCL were these few hundred lines from each of the kernels. And here are the performance results. We used it in CPUs, NVIDIA A100 GPUs and AMD Instinct GPUs. And all these versions are Cyclone generated versions. So that all starts from serial Fortran, and we generate the MPI and the OpenMP, OpenCL, OpenACC for it. So that's all automatically generated. And you can see we've been really targeting GPUs, and with OpenCL, we currently match the performance of OpenACC in NVIDIA, and it was the first backend that could target the AMD GPUs, because we were using unified memory in OpenACC and was not running very well on the AMD GPUs. We are now also building an OpenMP offloading target backend, so maybe we'll have soon more comparison points here. I've also calculated the in which percentage to the peak bandwidth we are, though that's a bit of a pessimistic calculation, because it looks currently how the kernels are. But really, if I could merge kernels, I could probably do better than this number would imply. But you can see that in the current MPI version of the CPUs and NVIDIA GPUs, we are doing pretty well. 60% peak of bandwidth, it's quite good. In AMD, maybe not so much. I've looked with the profiler, and apparently the L2 cache is much smaller than the one in NVIDIA, and I think it shares the instruction cache and the data cache in the same cache, I think. So hopefully adding some tiling, we can improve the results here. And also to mention that all these transformations can be done in addition to MPI, so we can do MPI plus OpenCL or all the other models. So we can run that. We've tried to run that in 2 nodes of 4 A100 GPUs in each node. Some other interesting things that we can do, we can do delay evaluation of runtime invariance. This is where we have like some arguments that we know, because we control the full parallel system layer. We know that these symbols, the symbolic arguments, are not modified during the whole parallel system execution. So we know that whatever value is there, it's going to always be the same. So we have this optimization called defined runtime variance that basically converts this into undeclared file scope symbols. And then during the compilation step of OpenCL, we can capture the value and give the compiler the value, so it can optimize these things much better. And this is some results of the code in this slide. Basically, it can reduce a lot the bytes sent in the CL set kernels arc. Though this looks a big difference, it doesn't really matter that much, because it just happens at the beginning. What it's really more important is that it can reduce the runtime of calling the kernel, and that happens every time you call the kernel. So that's a good improvement. However, it's a bit, it depends on the context if that matters. I tried this with a Nimolite application, and it didn't matter a lot, because it really memory bandwidth bound, and these optimizations were more, it helped for more compute bound applications. Another thing that we tried is we were part of the EuroEXA project, that's a European project to use FPGAs to do next generation HPC systems. So it was distributed FPGAs with MPI and some parallelism model to target the FPGAs. And because we had this OpenCL backend, we tried to, and Nimolite or Nemo was one of the applications being tested in this project. We tried to see how far we could get with our OpenCL backend, and we quickly realized that, well, we needed to do a lot additional optimizations compared to the GPU. One was adding functional parallelism, because we can have like multiple queues doing different things, because not everything is dependent on each other. We can duplicate kernels. We can inline the loops inside the kernel, so then the FPGA can pipeline the whole loop. That's what I'm calling Taskify. And it was also very important to do the memory reads and writes in bursts, so contiguous reads into local memory, and then work on that once it was loaded. Even with all of that, so the baseline without all the modifications, it was like 220 times slower than a single core CPU. So we started in a very slow baseline, and even with all these modifications, we are added together, we're at 15 times slower than a single core. So I wouldn't say it's competitive yet with CPUs and GPUs. Part of it is that because we are memory bandwidth bound, and the FPGA that we were running this on has 4 DDR memory banks, and we were just using one of them, so that already cuts our performance by 4x. And then we are also not using OpenCL pipes yet, so transferring from one kernel to another goes through memory. That's not the most efficient. So to try to be as competitive as CPUs, we probably need to continue doing optimizations, and I find it hard to believe it can be as efficient as GPUs at the moment. But yeah, maybe with a lot more transformations we can get there. Unfortunately, this project finished, so if we continue, this should be in another project. Yeah, and then the last thing that I want to mention is about the applicability of this solution to other applications and other domains. So if you can consider this spectrum from application specific to standard Fortran, I think what we currently have for Fortran to OpenCL applies basically to Cycle, this kernel-based model for Fortran that we have. And we probably can apply it to any Cycle application, but really we've just been testing it with one. So probably today we are here, but we have some work specifically in the Nemo code, which tries to do the same first with directives like OpenACC, but ultimately we can also do OpenCL with any numerical applications. And we do that by just parsing the code as it is. It doesn't need to be rewritten in Cycle format. And we infer where the kernels are. This is a view of our AR. It's probably too small here to see, but the important thing is this note here that it's called inline kernel that is automatically inferred from our tool. And we can infer it just by looking at the array notation, because then we can see that the computation is loop independent, or by doing dependency analysis, if we have explicit loop, we can do some analysis and verify that it's really loop independent, or if it's not, what's the dependencies. And with that, probably we can connect that with OpenCL for in the future be much more general applicable than where we are today. One problem with that probably is that this tends to make the kernels very small. So we have a lot of very small kernels. So I think we need a better way a model to fuse kernels together to make this efficient with OpenCL. Anyway, that's my last slide. To sum up, Cyclone is a source-to-source a transformation tool for Fortran that can do Fortran to Fortran or Fortran to OpenCL. That's useful because it can solve two problems. One is we can do a good separation of concerns between the science code and the parallelism and performance optimization code. And the second is that we can provide performance portability by giving different recipes to different architectures. And there's some future work that we can do. One is to continue generalizing this solution to other numerical operations and not the cycle model. Another, we can do more work on doing IR transformations for performance portability. As I said during the presentation, I think fusing and tiling are two of our next big steps here. And at the moment, we just use OpenCL as a backend. There is the possibility of using SYCL, there's some opportunities there, also some big challenges. But yeah, if the ecosystem is stable enough and all the tools are ready or do optimize SYCL better than OpenCL, we might consider going to SYCL instead of OpenCL. Yeah, so that's me.
Wonderful, thank you. Probably have time for one quick question. Over here.
Have you considered using MLIR infrastructures for that? Because the Flang is produced directly the AST in MLIR, and all the tiling infrastructure, all the transformation, even the executor with IRE targeting Vulkan or OpenCL is there.
So in the UK Excalibur project, there's people from Edinburgh University that are working from us to look at MLIR. There is two possible routes to MLIR. One is to still have our infrastructure and have a backend to MLIR and then continue doing transformations there and then go to the architecture specific, so be something plugged at the end. There is the other solution which we are not thinking yet, but might be an option to the future, is to build our own IR in top of MLIR, so Express on there. But yeah, we are exploring this. It's not going to happen soon, but maybe at some point. Yeah.
Thank you. Squeeze in one more quickly. Yep.
I love the name of the project. You already took the name that I wanted for this conference, Cyclone. So you already have SYCL in the name.
Yeah, it's Cyclone. Yeah. Yeah, it's similar name. Yeah.
Thank you. So we don't eat into the coffee break too much. We'll finish there. So let's thank Serge again. Thank you very much.